So if you are to consider our previous activity, it was actually having the formulas which are important working with our transient RC circuit. So we're not going to waste much time. This is simply some of the examples that we are going to work with as we are revising to understand the formulas that we had. Remember here when I presented RC circuit, and considering the formulas, is it when you are charging, when the source is connected, where you talk of the discharge cycle, when the source is now disconnected, the formulas that you need, and also calculating of the energy, and considering the condition of the rate of change, which can happen in current, which can also happen in terms of the voltage. And if you still remember, I defined the time constant of an RC circuit. So we're not going to waste much time. We just consider these questions that we are given. So what you need is to understand the state of the question. Is it on a charging or is it on a discharge cycle? That condition is very, very important to note. So in these questions that we are given, let's say the first question that we have, a capacitor, which is a 2 microfarad capacitor, is connected in series with a 20 kilo ohm resistor. So we are talking of an RC circuit. Okay, that's an RC circuit that we consider there, a resistor and a capacitor. So our capacitor value is, according to the information that we have got a capacitance of 2 microfarad, the resistance value, which is 20 kilo ohm. So this is 20 kilo ohm. Determine the following. Should a step voltage of 100 volts be applied to the circuit if the voltage is applied? So Vm, which is our VDC, is being applied. It is connected at that moment. So when it is connected, meaning to say the state that we are working with in this case is charging. You are charging the capacitor. So this is the charging state. So this is what you need to understand. If the source was already there, then you remove it. It is now discharging, because these formulas, they are different, as you can see, for a charging state and for a discharge state. So you're supposed to understand which one are you dealing with. So in this case, we saw that it's a charging. So our focus will be on these formulas, on the charging state, the charging cycle, the charging condition. So that is the major part that you're supposed to take note. All right, number one, the time constant, which is A. So remember that I say the time constant, considering that you are working with an RC circuit. The time constant is given as the product of the resistance times the capacitance value, meaning to say our tau, which is the time constant, that's the resistance, 20 kilo ohm, 20 times 10 to the exponent of 3, the capacitance value, 2 microfarad times 10 to the exponent of -6. So that is going to give us tau, which is our time constant of 0.04 seconds. So you can leave it like that. You can convert to milliseconds. It depends with the way that you actually understand. So to milliseconds, just multiply by 1,000 or 10 to the exponent of 3. Your answer is going to be in milliseconds, which is going to give you 40 milliseconds. That is, if you want to present it that way. That is the tau, the time constant. It's an RC circuit. B, the time taken for a capacitor voltage to rise to 90% of the final value. Okay, I think I discussed about that also. If we still remember when I was talking about a certain X percentage that can be given, that a capacitor voltage to rise to X% of the final value, it means VC is X% of VM. At that moment, it is rise. So it is given a certain percentage that it is going to rise to this percentage of the final value, which is the step voltage, the one that is being applied, our VM. Okay, that is our maximum voltage that we can have, our VDC. Okay, which is our VDC is given as 100 volts. So they are saying calculate the time. We need the time first. First thing, is what is to be calculated here. Okay, what is to be calculated? It is the time. But when the capacitor voltage, when VC is equal to 90% of the final value, 90% of the total voltage, 90% of VM. That is what they are saying. We have it. Are we not having? We have it. What is our VM? That is 100 volts that we are given there. So we're going to use the value that we are given there. So it's a state that must be considered, the percentage there. So remember I talked about the important percentage also when we are dealing with the time constant, when it is a certain percentage of 63.2%. That one, it's a condition that is of a time constant when it is 63.2% of the final. Remember, the time will be equal to the time constant when it is like that. But this one is not at that percent. It's at 90%. So do your normal calculations, all right? So that means our VC was going to be 90 over 100 times VM. And as we can see, our VM is 100 volts, our VDC. So you multiply to 100 volts, which was going to give us 90 volts. So this is the voltage that the capacitor is having, which is 90 volts. So the question is calculate time. This is our question. We are supposed to calculate the time. But what is it that we are given? Having VC, we are supposed to calculate time. Why? How is that possible? Okay, let's go back to the charging. Remember, we are on a charging state. If you check on the VC formula, there is time there. So they want you to use the VC formula because you have VC. If they stated something about VR, you're going to focus on VR. If they stated something about the current, you're going to focus on the current. So there your focus is on VC, the one that you are given for a charging state. What is the formula for VC? On a charging state. On a charging state, we saw that VC is equal to VM into bracket 1 minus e to the exponent of minus t over tau. So this whole part is in a bracket. So we can substitute whatever that you're given so that we can calculate our t. This is the one that we need to calculate the time. Remember, our question is on the time. Calculate the time. That is the question. All right. So calculating the time, we can substitute our values VC. Remember, that is 90. So 90 is equal to VM. Remember, our VM is the one that is 100 volts, the one that you're given before. Minus e to the exponent of minus t, the one that you need to calculate over what? Tau. Remember, you calculated tau, your time constant. The time constant is 0.04. So I'm talking about the tau. This, guys, these are just Greek letters, those alpha, beta, what. So it is the tau that we are seeing there. So you can substitute even this as 40 milliseconds. It's up to you. 40 times 10 to the exponent of minus 3. You can substitute as the 0.04. It is up to you again. So with this, we want to calculate t. We are back to our mathematics N4. Yeah, that is the maths N4 when you were dealing with exponents, solving exponential equations where unknown values are given, if you still remember that. Okay, so let's go back to our maths, guys. What can we do? We can divide by the 100 that we are seeing here. You can simply divide by this 100, divide by 100, what's the product there? So let's divide. That's 90 over 100, which is going to give us 0.9 on our calculator is equal to, you are remaining with 1. The one that is remaining can expand the whole bracket, meaning to say it's 1 times the whole bracket, which is 1 minus e to the exponent of minus t over 0.04. I need to calculate the value of t, but look, it is on E, and on that E, the E is carrying a negative. So let me avoid this E to be having a negative. So how can I avoid that? I can take it to the left-hand side so that it will be E to the exponent of minus T over what? 0.04, which is equal to, already on the right-hand side, there was a 1, then I have to take the 0.9 the other side. Remember your equations, guys. So it will be minus 0.9 because it was a positive there. So at this condition, we are having a to the exponent of minus t over 0,04, which is equal to 1 minus 0,9, which is 0,1. So actually there you can even not indicate this stage, guys. Just write 0,1 there because you can see that if you take this, it's going to be a minus. You subtract that. So the question is, how do we get rid of the E? Let's get back to our N4 mathematics. Remember, that was the stage when you were introducing a ln, the logarithm of a ln. Why introducing a ln? Because we do understand that the ln of E is equal to 1. Okay? Remember our N4 mathematics, that the ln of E is equivalent to 1. So by introducing the ln, which is our logarithm, this one, if we introduce it this side as a ln, and we also introduce a ln this side, what is going to happen? Remember a logarithm, the logarithm of a to the exponent of n is same as n log a. So the same thing, ln a to the exponent of n, it's n ln a. The exponent here will be dropped down. You drop that exponent. So it will be minus t over what? 0,04. Ln e, ln a, log whatever that you have. But remembering that we are dealing or we are working with a ln e, which is equal to 1. So if it is equal to 1, then that means there's no need for me to write that ln e. Understanding that mathematically, there's no need of you writing that stage. You just write the ln of 0,1 on the other hand. Just like that. So you must be careful on the simplification. Like if you write it, I'm not saying it's wrong because the ln is 1, so it's not going to affect anything. If you do not write it again, it's just the same. All right. So how can we find it, guys? We have now back to our normal equation. This is just a fraction. So let's do cross multiply. 1 multiplies this side. So it was going to be minus t is equal to 0,4 multiplies this. So it's going to be 0,04. The ln of 0,1. So definitely to find the t, I must divide by this -1 here. I must remove this -1, divide it. So it's going to be here because it was a negative here. You divide by it. So here it will be a negative, just like that. Okay. So you're going to have a negative here. So that's it, guys. You and your calculator there. So t is equal to what? Minus 0, this is just you and your calculator. So you can even simplify this on your calculator. That's minus. So you're going to have minus 0,04. The ln of 0,1. Close the bracket. So that's it. You can even round off to 3 decimal places depending with your simplification. Let's say to 3 decimal places, it's going to be what? 0,092. So that's our t, 0,092 seconds. So you're talking of the time frame, the time taken, the time that was taken which to have the VC at 90% of the final value. So you must find VC. And with the VC formula, is it of a discharge or a charging? We are talking of a charging state. All these calculations, remember, it is the charging state that we are talking about. So you use the formula of the charging state. All right. Let's see another question. Say the energy stored in the capacitor when fully charged. When it is fully here. When the capacitor, remember what I said on the introduction, when the capacitor is fully charged, your VC, it will be at 99%, but in the simplification of the theory part, you take it at 100% at VM. So when it is fully charged, VC is equal to VM when fully charged. When fully charged, remember you're charging, it will be at the equivalent value of your VM, which is your VDC. They will be equal. So if that is the case, they are saying the voltage across the capacitor is equal to VDC, which is 100 volts. If that voltage is 100 volts, calculate the energy stored in the capacitor. Remember, I talked about this also on our introduction, that the energy can be calculated from which formula? The energy is 0.5 CV squared, which is half CV squared, the voltage across the capacitor, which is equal to Vm. Remember, I told you guys to use the condition that you're given there. So that's it, guys. So we're going to calculate our energy. That's half. Half is simply 0.5. I mean, that 0.5 is the same as half. So it's half of V squared, but the voltage of the capacitor. So it's half of the capacitance value. What is our capacitance value? That was 2 microfarad. So that's 2 microfarad times 10 to the exponent of negative 6 VC, which is 100 volts. So with this, you are going to obtain your energy being stored in the capacitor. All right, this is squared there. All right, so you're going to square this. That is going to give us something like 0.01 joules. Remember, you're talking of the energy. So that is going to be in joules. Just like that. Please be very, very careful. The condition of the person, how it is given, just like that. Let's move on to another part. They are saying on D, the initial rate of change of current. Remember, rate of change. The moment you see rate of this one, the rate of change. No, let's not talk of initial. We're going to talk about that later on. Rate of change of what? The rate of change, considering current, the rate of current change. I said, from the current expression formula that you are given, is it voltage? The one that you are given, the rate of change, if it is current, the I dt. If it is voltage, dV is T, voltage with respect to time. But initially, when there is an initial condition, there you use T is equal to 0. All right, and I explained how to differentiate this, guys, remember, from our exponent condition. All right, so what is the current first? How do you write the current formula? When charging, remember IM is equal to IM e to the exponent of minus T over tau. This one when charging. So that is the formula for current. With that formula, we are going to use it now to determine the rate of change, which is the I dt. So let's find that. The I dt. The moment you, guys, this is where mathematics plays a role. The moment you differentiate current with respect to time, that's a rate of change that you're finding. That's the rate of change of current. So what is the derivative? Remember, it is with respect to what? With respect to time. So everything here, which is not t, becomes a constant. What am I trying to say? Everything that we see on this other side, which is not t, becomes a constant. Im becomes a constant. Minus 1 over tau, this one, it becomes a constant. Remember, this is minus t over tau. So it's like minus 1. There's a 1 there that is affecting. So that minus 1 over tau becomes a constant. So the question is, how do you differentiate t? Remember, it's supposed to be the first derivative of this t that we are given. Okay? First derivative of t times e to the exponent of that f of t. That's how you can differentiate e to the exponent of f of t. You need this. So what is the derivative here of minus t over 1 pi, over 1 tau, this one? Remember, guys, the same as minus 1 over tau times t. So when you differentiate, you are taking this one. You just drop this one. That is the derivative here. But it must multiply Im. Take note, there is Im there. Okay, so this is how it is actually like presented. So the number there is minus 1 over tau that you need, all right? So that is how it is going to be like. So it's going to be Im times, you drop the exponent affecting t which is minus 1 over tau. So this was going to give us minus, okay, if you multiply this, minus Im over what? 1 times tau, which is tau. So this is what you're going to have, e to the exponent of minus t over tau as it is. The e to the exponent of f of t remains as it is, guys. This is how you differentiate e from our mathematics. Even in our N6 maths, we still have that. So you must be very used to that, okay? Anyways, just for revision's sake, that's how you're supposed to differentiate your e. Derivative that is affecting t, you multiply to the already value that is there. So if we check, they said initial, that is where now we go back to the initial condition. Initially, t is supposed to be equal to what? To 0. When you are starting at the starting point. So meaning to say, we can now determine this rate of change of current numerically, having the numerical value, like what is the answer now? This was a presentation of the rate of change of current. But what is that initial? What is the exact value when initially our time is at 0? So we're going to substitute what is Im. These values, Im, are we having this? Oh, we never calculated Im. Okay, so we can calculate that. Remember Im from the resistance value and our VDC. Oh, guys, now I'm showing something that you're not even supposed to see. All right, anyways, very sorry for that. This you're not even supposed to see it. Anyways, it happened. They say it happens. All right, anyways. So in this case, like I said, we need to calculate Im. We do not have it on our formula. Just have to see now, okay, this is my formula, but what is it that is missing? Tau is already there. Remember, we calculated this. Tau does not change, the one that you calculated. So it is only Im that we need. And Im, like I said, that is Vm over the resistance. And Im is equal to Vm, which is 100 volts. This one over the resistance value 20 kilo ohm, 20 times 10 to the exponent of 3. Yeah, 20 kilo ohm, 20 times 10 to the exponent of 3. So that was going to give us Im, which is going to be 0.005 amperes. And you can write this in milliamps by multiplying by 10 to the exponent of 3 or 1,000. That is going to give you 5 milliamps as your Im. So guys, remember it's a value to be used. So changing these to milliamps does not even make sense. Just write that value as it is. So Im is there. So that is minus 0.005 over what? Tau, our time constant, 40 milliamps, or this 0.004, the one that we calculated. E to the exponent of what? Initial, even if I do not know the value of that, it's only that it affects here, but this one, e to the exponent of minus 0 over the value, whether the value is big or small, guys, it will give us a 0 because of that 0 in the numerator. 0 over k is what? It gives us a 0. So that means we are going to have e to the exponent of a 0 here, where e to the exponent of a 0 is what? Is 1. Or just use your calculator, guys. So this is going to give us minus 0.125 if you divide these two numbers. That is ampere per second is the rate of change. Ampere per second. Some textbook, they can use ampere per second like this. Still one and the same thing. The rate of change. The rate of change. What is it that is changing? Is it voltage? You consider from the voltage. Is it current? You consider from the current. So that's how questions can be given as. Let's check another part still on our questions. Determine the following. Should a 20 microfarad capacitor be charged through a 30.3 kilo ohm resistor? So we are given that it is supposed to be charged. It is supposed to be charged. That is the charging state. We are still on the charging state or the charging condition. Given a capacitor that has got a value of 20 microfarad and the resistance value connected in series is 30,3 kilo ohm, and the VDC that we are given, which is our VM, is 60 volts. So VDC. The question is calculate, determine the initial charge. Guys, be very careful. The initial charging rate. Yeah, there, rate. There is a rate there to be considered. The moment they talk about the rate, what is it that you charge on the capacitor? Definitely, you talk of what? VC on the capacitor voltage. But they want the rate of change. We are back to dV dt. The rate of change. We are back again. So this is our A. Remember, VC is given. VC is given by the formula. This is a charging state. Okay, let's go back to our formulas so that we do remember. VC, this is our VC on a charging state. So taking our VC into consideration, let's see. Okay, so VC is equal to what? Let's substitute. VC is equal to VM into 1 minus e to the exponent of minus t over tau. This was supposed to be the formula to be used to calculate the voltage, but they do not want that. They want a rate of change, where a rate of change is now the derivative of what is given there, which is dVc, with respect to time, always with respect to time. So you must find the derivative there. Okay? You must find the derivative. Okay, so let's focus on differentiating this. How can we differ before we talk of what is missing? How to differentiate, that's another thing on its own. So as you can see, there's a bracket this time, so we can simply expand the bracket here. Remember, I said with respect to time, everything becomes a constant, but let's expand the bracket properly so that we can see Vm times 1, that is Vm times this, that's going to be minus Vm e to the exponent of minus t over tau. Okay, we need to differentiate in this case the derivative of V with respect to time, VC, capacitor with respect to time, where with respect to time, I said everything that is not part of, that is not T as a constant, meaning to say the VM that we are seeing here, and this part of minus 1 over tau, the one that I explained before, is a constant. They are constant. These ones, they are constants. So worse enough, the first one, we do not have a T. If it was like this, maybe there was a T here. Okay, let's say it was Vm times T. And you want to differentiate with respect to T. It means your answer was going to be Vm. Why? Okay, let's go back to our mathematics, guys. 3x, the derivative of y with respect to x like this, you just take a 3. Okay, remember, this is to the power of 1. But if you are given y is equal to 3 and you're asked to find the derivative of y with respect to x, what is your answer? That's a 0 because 3 is a constant. So the derivative of a constant when the variable is not there, is just a constant on its own. The answer is a 0. So to differentiate Vm with respect to, there is no t here. With respect to t, there is no t. So it's a constant on its own. There's nothing. So its derivative will give us a 0. Okay? Then we differentiate this part of E, this one. Remember, I talked about this E, guys. You drop the exponent, this one that is affecting T, and it multiplies the Vm. There's nothing that has changed. It's only there we are using what? We're using current. This time, there is minus Vm voltage. So it's minus Vm times, we drop the exponent on T there, which is minus 1 over tau. So that was going to be what? Minus. That was going to be a plus. So it was going to be plus Vm over what? Over tau. 1 times t, 1 times tau, which is tau. E to the x, this E remains as it is. E to the exponent of minus t over what? Over tau. It remains as it is. So this is our rate of change, guys. 0 plus means that there is nothing there. Okay, so you're going to just remove this 0 here. 0 plus, there is nothing there. You can write that stage. I'm not saying it's wrong. It was just for us to know what is happening. So that's our rate of change. We have rate of change, or VC. This is the expression for that. But the question is not just on the rate of, they're saying initial. Now, initial. Once this is there, we are starting from where? Where are we starting? That's the initial. Initial from where you are starting. Your starting point. So your starting point is always when time is equal to 0. So that's the initial condition. So initially, remember, time is equal to 0 seconds. So the time is 0 there. So mean to say, in place of time, we are covered. What about VM? Do we have that? VM, remember we're given, that's our VDC. What about tau? Are we having that tau? We do not have. So VM is there, but we do not have the tau. So you're supposed to find tau. It's an RC circuit. So tau can be calculated. The time constant of an RC circuit, RC, R times Z. So that's our tau. Resistance times capacitance. Resistance, 30,3 times 10 to the exponent of 3 times the capacitance value, which is 20 microfarad. 20 times 10 to the exponent of -6. This was going to give us the value of tau, which is round off to 3 decimal places. It was going to be 0.606 seconds. So we have the tau, a time constant. With that, we can substitute in place of everything that you're given, whatever that we have, and find the rate of change. Remember, that's the rate of change there, which is equal to VM. Remember our VM, 60. So that's 60 over tau, which is our tau is what? 0.606. E to the exponent. Remember, guys, this is 0 there initially. So that's e to the exponent of a 0, which is simply a 1. So 1 times this is going to give us what? 60 over 0.606. This one is going to give us 99.01. That's volts. Remember, it's voltage per unit time. So it's volt per second. Volt per second. Or you can write as volt per second like this. That is how the question can be like. You see, guys, they want to test you. Rate of change. They will try by all means to disguise you guys. So be careful as you present. Okay. Anyways, let's see another question. So tau, we're gonna need this. Let's just write aside. So remember, our tau, the time constant when we're calculating, it was 0.606 seconds. Maybe we might need it somehow or somewhere. Let's see on B, the time taken for the voltage across the resistor to decrease. Take note. Take note. B, we need the time. That's the first thing. The time for the voltage across what? The resistor, VR, to decrease to, there are questions like it can decrease by or to. When it is 2, it means it is at that percentage. VR is equal to 30% of VDC. Our VM, that's our VDC. It's at that voltage. You're told guys about VR. Calculate it. Calculate that. Find it. Because there's a condition about VR. So let's calculate it first. 30%, that's 30 over 100 times VDC, which is our VM, 60 volts. So if you multiply this, you're going to obtain 18 volts. That's 30% of it. So they are saying calculate or determine the time in that period. What is the time? That's the question. That's the question. The time in that period, like the time taken for voltage to decrease to that. So let's go back. Remember the state that we are dealing with? It's a charging state. So VR under a charging state is written as what? VR is written as Vm e to the exponent of minus t over tau. Remember your formula is charging state. So let's have our formula. for VR. So from that, our charging state, VR is equal to Vm e to the exponent of minus t over tau. Remember, that's charging. So let's substitute. Our VR is 18. 18 is equal to Vm or VDC, 60 e to the exponent of minus t, the time, the one that you want to calculate, over tau. Are we having tau? Remember, we calculated tau before when we calculate in the first equation. So you do not calculate again and again and again something that you have. You can substitute that. All right, so let's calculate the value of t in that case. I think we talked about this similar question where the exponent equation is to be considered, where the e is. Okay, let's get rid of the 60. There's nothing to do with this 60, guys. Just divide by this, the product. So simply divide by 60. That was going to give us 0.3 equal to e to the exponent of minus t over 0.606. So there, I'm not going to waste much time. I talked about this, guys, how to remove this from an e that we are given. You introduce ln, a logarithm. You introduce ln, a logarithm. Meaning to say the moment you introduce a ln, a logarithm, what is going to happen, guys, on the right-hand side? Okay, sorry for that. I wanted to remove this. This is the ln of 0.3. What is going to happen here on the right-hand side? You simply drop the exponent as it is. So it's minus t over 0.606. The ln of e, you drop it as it is. You are not differentiating. These are your exponents. But you remain with the ln of e, which I said is 1. So it simply means there's nothing there. So this is what you're going to have. So let's find t, guys. Going to cross multiply, definitely. So that will be t is equal to, if you cross multiply here, it was going to be 0.606, the ln of 0.3. So it was going to be minus t. But for you to remove the minus here, because it's minus, there's minus t there. To remove that minus so that it becomes a positive t, the minus will be affected this other side. So that will be the value of t. So that's it, guys. We can calculate our t from there using your calculator. Your t was going to be 0.73 seconds. The time now, you're talking about all time considered. To have our VR at 30% of what? Of VDC. All right, just like that. C, the charging current after 75 milliseconds. That's C. The charging current after 75 milliseconds when the time is 75 milliseconds. When the time is 75 milliseconds, what is our charging current? The charging current. So it's just a matter of substituting. Remember, we are still working with our charging state. And under that, the charging current, it's Im. E to the, there is just direct, guys. It was just a matter of substituting into the formula. I is equal to Im e to the exponent of minus t over tau. Within the time frame of 75 milliseconds, we are given the time. Okay, the tau, we already calculated this. Remember, your tau is already there. So these are there, but we do not have Im. The current from maximum condition values that we are given, we can calculate Im. Remember that Im is equal to what? Im is equal to Vm over R. So from the voltage and resistance, Vm 60 volt over the resistance, our resistance 30.3, that's 30.3 times 10 to the exponent of 3. So that was going to give us Im, which is our current. That was going to be 0.00198. I just need 3 digits there. You can write in milliamps, microamps, 1.98 something microamps, milliamps, which is fine. Okay, I'm just going to take this value, guys, this one as it is here. That is our Im. So with this Im, we're just going to substitute to calculate the current. So Im is what? That's 0.00198 e to the exponent of minus t, the time given, 75 milliseconds times 10 to the exponent of 3 over tau. Remember, we calculated tau before. Our time constant, tau here, it was 0.606. So it was just a matter of substituting this one, 0.606. With your calculator, you can simplify this. You're going to get 0.00175. Okay. All right. I knew it's going to be like that. Anyways, let's